Dear audience, I am Professor Dr. Engineer Jesús Toribio from the University of Salamanca in Spain. This is the beautiful logo of my university, the University of Salamanca, the oldest in Spain and one of the four oldest in Europe, Bologna in Italy, Oxford in UK, and Paris in France being the other three. The logo consists of the castle, lion, and the bishop. Castle and Lion, the foundation of modern Spain. The title of my presentation will be Sculpture and Fracture Mechanics. The outline consists on 8 parts: introduction, cold drawing of perlitic steels, microstructure evolution during cold drawing, hydrogen embrittlement of progressively cold drawn perlitic steels, hydrogen-assisted microdamage HAMD evolution, discussion about virtual cold drawing, scientific conclusions, and closure between Donatello and Michelangelo. First of all, the introduction. Motivation. Fabrication of high-strength prestressing steel wires is made by cold drawing. As a first consequence, there is a progressive orientation of the two basic microstructural levels, perlitic colonies and lamella. And second consequence, there is an influence on the fracture and structural integrity. Then the aim of the work is twofold. Firstly, from the scientific point of view, it is a material science approach to the fracture phenomenon, relationship between microstructure and macroscopic behavior. Secondly, from the art point of view, exploring the relationship between sculpture and fracture mechanics, that is, the relationship between science and art. There is a key question. Is the cold drawing process beneficial from the hydrogen embrittlement point of view? Let's describe the cold drawing of perlitic steels. Two pictures of the real manufacturing chains in the industry with progressive cold drawing, passing of the perlitic steel wires through several dies, with the consequence of an increase of yield strength and UTS, ultimate tensile strength, by a strain hardening mechanism. This is an schematic of cold drawing of perlitic steel, a typical process of 6 passes through 6 dies, and a 3D view of this process. Third, microstructural evolution during cold drawing. Regarding perlitic colonies, first microstructural levels, we have pictures of the metallographic analysis, perlitic colonies of steel 0 degree of drawing, hot rolled, not cold drawn at all, steel 3 after 3 steps of cold drawing, and heavily cold drawn steel 6 after 6 passes through the dies. While the steel 0 exhibits a randomly oriented microstructure with randomly oriented perlitic colonies, there is a slight orientation in the vertical direction of the micrographs, cold drawing of y-axis direction in steel 3 with an intermediate degree of cold drawing, and finally in steel 6, heavily drawn steel, commercial precision steel wire, there is a markedly oriented microstructure regarding perlitic colonies in a parallel direction to that of cold drawing y-axis or vertical direction of the micrograph. Regarding the evolution of perlitic lamella, second microstructural levels, again we see randomly oriented lamella in steel 0 degree of cold drawing, a slight orientation along the y-axis direction, vertical side of the micrograph or cold drawing direction in steel 3, and steel 6 heavily markedly oriented microstructure in the direction of cold drawing. It's a microcomposite with lamella, it's like a laminate with the lamella oriented in the vertical direction of the micrograph, that is, in the direction of cold drawing y-axis. Summary of microstructural evolution during cold drawing. First, a progressive orientation and slenderizing of the perlitic colonies, first microstructural level, and In addition, a progressive orientation of the ferrite cementite lamella, second microstructural level, and decrease of interlamellar spacing. As a summary, orientation in the drawing direction and increase of packing closeness. Fourth part, hydrogen embrittlement of progressively cold round perlitic steels. This is the fracture profile in hydrogen-assisted cracking. From 0 degree of cold drawing, slightly drawn, intermediate degree of cold drawing, and heavily drawn. On the left-hand side, we have mode 1 propagation in a slightly drawn steel, mixed mode propagation with a small component of mode 2 in the intermediate degree of cold drawing, and mixed mode propagation with a strong component of mode 2, a propagation step almost in vertical direction in the most heavily drawn steel 6. At the bottom, we have the 6 profiles of fracture for the 6 degrees of cold drawing, 0, 1, 2, 3, 4, 5, 6, evolving from only mode 1 to mixed mode with slight mode 2 to mixed mode with a strong component of mode 2 and a marked deflection angle almost close to the 90 degrees in relation to the original propagation direction in mode 1. Then we have a progressively anisotropic hydrogen-assisted cracking hack behavior with cold drawing. A model of this behavior. We have material anisotropy, again twofold, regarding two aspects. Firstly, strength anisotropy or mechanical anisotropy. K1C is a directional function, a directional property as a function of the propagation angle. For a propagation angle of 0 degrees, that's mode 1 propagation, we have K1C for 0 degree for fibers fracture, transverse fracture. For 90 degree propagation steps deflected 90 degrees from the original mode 1 propagation, we have K1C parallel, K1C for theta 90 degrees for longitudinal splitting. Then we have K1C perpendicular, quite higher than K1C parallel due to the mechanical anisotropy. In addition, we have chemical anisotropy for hydrogen diffusion, D perpendicular for 0 degree of diffusion in the transverse crack direction, and D parallel for 90 degrees, diffusion in the longitudinal direction parallel to the fibers. D parallel is quite higher than D perpendicular. Opposite to the K1C perpendicular is quite higher than K1C parallel. Then micromechanics of hydrogen-assisted cracking, we have preferential hydrogen diffusion and lower fracture toughness in the cold drawing direction. Preferential D parallel diffusion parallel to the plates, parallel to the fibers, and a slower hydrogen diffusion perpendicular to the plates, perpendicular to the fibers. Then we have hydrogen-enhanced decohesion, delamination or debonding, HEDE, between two similar microstructural units, either colonies or lamella. Hydrogen-assisted microdamage, HAMD evolution. Fractographic analysis for steel 0, hot rolling, not cold drawn at all, 0 degree of cold drawing. We have a kind of hydrogen damage topography after the fatigue pre-cracking, and final fracture by cleavage. This hydrogen damage topography is the so-called tearing topography surface with a kind of microdactyl behavior, a kind of ductile appearance at the finest microstructural level. With regard to steel 6, heavily cold drawn, commercial pre-stressing steel, we have again hydrogen damage topography deflected almost 90 degrees in relation to the original mode 1 propagation, fatigue propagation in mode 1, a kind of enlarged and oriented tearing topography surface. We have also TTS, tearing topography surface, but with a clear orientation and enlargement in the deflection direction in the direction of cold drawing or y-axis. After this hydrogen damage topography, enlarged unoriented, we have classical microvoid coalescence and final fracture unstable by cleavage. The summary of fractographic analysis, summary of fracture modes in steel 0, hot rolled, 0 degree of cold drawing, not cold drawn at all. We have hydrogen damage topography, HDT 0, in the form of tearing topography surface, TTS. In steel 6, heavily drawn, commercial precision steel, we have HDT 6, very deformed TTS, very deformed tearing topography surface. And from steels 1 to 5, HDTI, progressively deformed TTS. Then we have a topography of the kind of enlarged and oriented TTS, EOTTS for the most heavily drawn steels. And the apparent deformation observed in the fractograph corresponds to a direction close to the axial one, cold drawing direction. Then discussion about the phenomenon of virtual cold drawing. Discussion and summary of fracture mode. We have HDT fractographs and hydrogen-assisted cracking mechanism. Then the HDTI, for different levels of drawing, is increasingly deformed with cold drawing. And the deformation is oriented in the cold drawing direction. Then the question arises about whether or not a geometric relationship does exist between the HDT modes so that one can be virtually obtained by deforming a previous one associated with a lower degree of cold drawing up to a certain level of virtual strain, a sort of virtual drawing. This is the schematics of this virtual cold drawing in the direction of the fractograph. Then, with computer-assisted analysis, we take a fractograph, a real picture, a real fractograph of a steel 3 after 3 cold drawing passes, 3 steps of cold drawing, 3 passes through the dies, number 3, and this is the enlarged fractograph of a hot rolled material, steel 0. This is a virtually obtained number 3 coming from a 0 level of cold drawing. We have similar appearance of the real fractograph of steel 3 and the virtual fractograph of 3 coming from computer enlargement of number 0. The same for steel 6. This is the real fractograph of steel 6, enlarged unoriented TTS, enlarged unoriented tearing topography surface. Left-hand side of the slide is real number 6 fractograph, and this is an enlarged, virtually enlarged by computer-assisted enlargement fractograph of number 6 taken from number 4. Then number 6 coming from an enlargement of steel number 4. You have similar appearance. You can observe they are really similar, real number 6 and virtual number 6 by enlargement of real number 4. Then real number 6, 6 steps of cold drawing coming from a steel which has undergone 4 stages of cold drawing. Then finally the scientific conclusions. Important microstructural changes produced by cold drawing which affects hydrogen-assisted cracking behavior. Second, progressively anisotropic hydrogen-assisted cracking hack behavior as the cold drawing degree increases. And finally, there is a geometric relationship between the different HDTI, the different hydrogen damage topographies for different levels of cold drawing as a sort of virtual cold drawing of the fractographs. And now the closure, a relationship between science and art between Donatello and Michelangelo. Between these two Italian sculptors, Donatello and Michelangelo. For a slightly drawn perlitic steel, the fracture mode is tearing topography surface, and it resembles the texture of the surface of Michelangelo stone sculpture texture. Here I present Pietà di Firenze in the Museo dell'Opera del Duomo in Firenze, in Florence, in Italy. This beautiful is the second Pietà of Michelangelo. Then, this Michelangelo's Pietà di Firenze can be classified as Michelangelo stone sculpture texture, MSST, resembling the so-called towering topography surface in not cold round, hot roll, or slightly drawn perlitic steels. Another beautiful picture, beautiful example of Michelangelo's structure resembling a slightly drawn perlitic steel fractography in hydrogen-assisted cracking conditions is Michelangelo Pietà Rondanini in Castello Sforzesco in Milan, Italy, La Italia. This Michelangelo Pietà Rondanini represents Michelangelo's stone sculpture texture with a kind of roughness which resembles the tearing topography surface. This is the hydrogen damage topography in slightly drawn steels, or not cold drawn at all, hot rolled materials. In the matter of heavily drawn perlitic steels, I am presenting the Donatello Penitent Magdalene, a beautiful work with a kind of tearing. It's an arrow to your heart, a freccia in el cuore, in Italian, an arrow in your heart, a kind of psychological tearing and surface tearing, resembling Donatello Penitent Magdalene, resembling the enlarged and oriented TTS, enlarged and oriented tearing topography surface, with a kind of not only physical but psychological tearing, soul tearing, and it represents Donatello wooden sculpture texture, DWST. Again, for heavily drawn perlitic steels, I present in Donatello St. John the Baptist in the Venezia Chiesa dei Frari, and again a kind of tearing resembling the so-called enlarged and oriented tearing topography surface associated with the fractography of hydrogen embrittlement of the most heavily drawn perlitic steels. This Donatello St. John the Baptist represent the Donatello wooden sculpture texture, DWST, linked with the enlarged and oriented TTS in the most heavily drawn steels. As this conference, EGF 27, is held in beautiful venue of the University of Rome, Roma La Sapienza is really close to San Pietro in Vincoli, where the beautiful Michelangelo's Moses is located. Again, Michelangelo stone sculpture texture, MSST. Of course, I recommend the visits a short distance from the conference venue. In San Pietro in Vincoli, in which we have this Moses Michelangelo stone sculpture texture, MSST. And with the beautiful logo and the letters of the University of Salamanca, Campus of International Excellence, I finish the presentation. Thank you very much for your kind attention. That's all.